Okay. All right. We'll see how this goes. Hope you all have umbrellas. I was an undergrad, junior year, first day of classes. I heard it might rain, so I brought an umbrella. But it turned out to be a nice sunny day, and then I ended up leaving an umbrella in class. So then I bought another one, and then when I went to expect to that same class where I left it on the phone. So I left it there on Monday. So class on Wednesday, one of my classmates had given me back the umbrella, so now I had two. Later that day, I left both of them in class. So yeah, I'm just being umbrellas. Okay, so one of the things that I'll cover today will actually be the subject of the first homework problem. So you'll be able to jump into that. One thing you should keep in mind, you'll see when you go to the homework assignments in Canvas, there's a PDF file that has the questions in it, and then there's another one that's hints. And there's something, information there for each problem. Definitely take a look at that. That will anticipate a lot of questions that I've gotten from previous instances. So, okay. Now, last time I finished with notions of solutions. When do you have a classical solution, or when is it a weak solution? And looked at some examples of that. I have one more example from there. And as I've mentioned this PDE before, Berger's equation. Okay. That's t plus, say, 1/2 u squared, that's nonlinear, and all that with respect to x. That's the same as ut plus ux is equal to 0. And what happens here is, if we suppose the initial condition, u of x0 is u naught x. And suppose, under the ideal circumstances, we have u naught in C infinity. Someone tell me, this notation was introduced last time. What does it mean when we say a function is in C infinity? What do we know about it?
So derivatives exist. You can differentiate it as many times as possible.
That has infinitely many continuous derivatives. So it's infinitely smooth. So best possible circumstance. But even if that's the case, what happens is u of xt eventually becomes discontinuous. Discontinuous. So, whoops, that's spelled wrong. Discontinuous. So if the solution of a PDE, even this one, this is a first order PDE because we have at most first derivatives in it. So if a solution is discontinuous, then what kind of solution, what do we call that? There are two notions of solutions. Which one applies here? Yeah, it's a weak solution. So u is not even in C0 eventually. It would have to be in C1. So one continuous derivative. So it actually falls 2 degrees short of being a classical solution. Okay. All right. Now, I have very little notes for today. And here's how I'm going to fill the time anyway, by doing things that are off script. But still relevant. Because I want to see if I can show you off the top of my head why this happens. And if it goes wrong, well, you have my disclaimer. So, and it's something I can fix up later. So what I'm going to attempt to do, and I always say that the first rule teaching anything unscripted is going to go wrong. And I violate that rule so many times. Not so much in lower level classes. I figure you're in Math 721, y'all can handle it. So, okay. Solve this PDE using something I teach in Math 417, 517. Method of characteristics, which is useful for a first order, especially quasi-linear equation like this one. All right, so method of characteristics. I have ODEs to solve. So I'm going to do a change of variable where instead of variables x and t, I'm going to have variables tau and s. So the variable tau is an independent variable. Independent variable tau identifies a particular characteristic curve. Variable s indicates as a variable for going along a given characteristic curve. So I'm going to rewrite the PDE as du dt dt ds plus u, just kind of playing the role of a coefficient, u dx dx ds, which amounts to du ds is equal to 0. Okay. Now, if I match this PDE against the original, what that tells me is, gives me a system of ODEs. dt ds is equal to 1 because we only have ut by itself. And then whatever's multiplying du dx, that's dx ds. So dx ds is equal to u. And then du ds is equal to 0 because all of this is equal to 0. So really I have these three ODEs that I now have to solve. So system three ODEs. All three of these will have initial conditions. So since our initial condition is imposed along the x-axis, which is the usual, I'll have x of 0 is equal to tau. This is unusual notation, or you might not have seen this before, but it is something that happens now and then. Like I normally I would say x of 0 equals tau. I'm saying s equals 0 just so you can have clarity as to which variable I'm setting equal to 0. And then t at s equals 0 is equal to 0 because we're on the x-axis where time is 0. And then finally, u at s equals 0 is equal to u naught of tau. Being a little sloppy here, x, t, and u are functions of s. They're also functions of tau, because s and tau are independent variables now. So now we can go ahead and solve our ODEs. But we have to be careful because here dx ds is u. U is also a function of s and tau, which is unknown as of this moment. So I don't really know how to solve this one yet. But I can go ahead and solve the other two. So t, I can just integrate this. dt ds is equal to 1, so t is equal to s plus a constant of integration. But when s is equal to 0, t is equal to 0. So t is just s. So we have that ODE solved. This ODE is trivial. Du ds is 0. That means that u is not a function of s at all. If we integrate both sides of this, u is just, you can think of it as a constant, but really it's something that isn't a function of s. It's the initial data. So u is equal to u naught. Okay. So now that u is not a function of s at all, I can take it into account here. And I can integrate both sides, because now that I know what this is, so x is equal to us plus some constant of integration. Well, when s is equal to 0, I'm supposed to get tau. So tau is the constant of integration. So all three ODEs are now solved. So that's what the characteristics does. Any questions about how these ODE solutions came about?
I have a question about the second one.
This one?
Yep, where did we begin? I am a bit lost. Which condition did we use to derive that?
Okay, so du ds is 0, so u is something that isn't a function of s.
Okay.
Then we go, and so that means, because u is never changing, that means it's always equal to its initial value.
Okay, u tau. Okay. However, u is a function of tau.
It is a function of tau, yeah.
Okay. That's it.
Okay. Anyone else have a question? So I kind of sort of have my solution, except except it's in wrong variables. I want a solution u of xt. What I have is u of s tau is equal to u naught of tau. So if I have u of xt is equal to u naught of tau, but the problem is I have to write tau in terms of x and t, and then I will have my solution. So to rewrite tau in terms of x and t, I look here at my relationship x is equal to us plus tau. So I can take this here and solve it for tau, and I get x minus us. But s, I don't want s either. S is t though. So I get u naught of x minus ut. So this is my solution. So it's the initial data that you're given, but it's evaluated at x minus ut. And the problem with that is we have u on both sides of the equation. So this doesn't really define u, it implicitly defines u. So this is an implicit solution. So if I was given a specific u naught of x for my initial data, I could attempt to solve this equation for u of xt. Chances are I wouldn't be able to do it, unless u naught was a particularly simple function. All right, so, but even though it's implicitly defined, I can use this to try to give you an idea as to why, even if u naught is a very smooth function, u of xt is eventually going to become discontinuous. All right, so that's what I'm about to do. So before I do that, are there any remaining questions about what I have here so far? Oh, okay, I see the thumbs up in the email, thanks. So what I'm going to do is I'm going to use this implicitly defined solution and try to get a handle on du dx. Let's try this. Oh, I got to take a picture, but actually I don't because I'm recording this and I can take a screenshot of that. I will want to work this into the notes later. Okay. So now I have, all right, so from u of xt is equal to u naught of x minus u of xt t. I'm going to differentiate both sides of the equation with respect to x. So we'll get ux on the left side. And on the right side, we're going to get u naught prime. So u naught is a function of only one variable of x minus ut. And then I have to take the derivative of what's inside with respect to x. That's going to give me 1 minus ux t. So now I have this equation that I can rearrange and isolate ux. So I'm going to go ahead and do that. I can't remember how it's supposed to turn out, but don't have it memorized. So, okay, so I can take all the ux terms and move them to the left side. So I'm going to have prime x minus p u t, not substitute, times t equals u naught prime x minus ut. So now I have u dx is equal to u naught prime up top all over 1 plus u naught prime x minus ut. And what we see here is and when it happens will depend on the particular choice of initial data. But what will happen eventually is that this denominator becomes 0. And so what ends up happening is, like, as time moves forward, the solution is propagating to the right, because this indicates propagation. It's a shift of a graph, but what it's shifted by varies over time. And you have different parts of a solution shifting at different rates because u is varying with time. If you think of what's multiplying t as the speed of propagation, what can happen is that some parts of the solution may overtake others, and you have the solution ends up having a slope that gets steeper and steeper, eventually becoming vertical. That's actually called a shock. And when that happens, we get 0 in the denominator down here. Ux du dx becomes infinite. So this is the kind of behavior that you can expect from a problem like this. And this is why, at best, we have a weak solution. It may be a classical solution for a while, but there's going to be some value of t at which it no longer is. And as you can imagine, this poses a lot of difficulty for numerical methods. In fact, when I'm using my numerical methods to solve problems like this, we might have some theory that indicates when the solution is going to blow up. And so my numerical method is not going to go past that point. It's going to try to solve it up to that point, and the closer we can get to it, the better. But once this becomes 0, all bets are off. The numerical solution is not going to happen.
Okay.
At least by conventional methods, like the kind of methods you're going to see in this class. Now, one of my PhD students, Chandler Shimp, is been working on a very interesting project where, for a variation of this equation, um, the solution u of xt is known to become multi-valued. In other words, not even a function. So for a given, at a certain time, at a certain x, you could have more than one u value. The solution actually turns over itself. So at first it might be behaving like this, still a nice function, but eventually it could behave like this. So it's actually called gradient catastrophe, but also like overturning because it loops back. Ordinary numerical methods cannot compute a solution like this because whatever they produce is going to have to be a function of x. But our method uses method characteristics where you're trying to solve for an equation that can have multiple roots in a situation like this. So her method computes all of them, therefore it's actually able to produce the multi-valued solution. So that's a rather unusual case, but a very interesting one. And that sort of thing that typical numerical methods are designed to handle. Okay, so questions about anything that happened here? Oh, for something unplanned, it went pretty well. Because I didn't screw up. that's the criterion. Okay, so now for the main topic of the day that plays into the first homework problem. Fourier methods. You may remember from your first PDE course that Fourier series play a key role in solutions of certain PDEs, and we're going to see quite a bit of those. Okay. So you look at selected initial value problems. So we're going to see in this class initial value problems where you have initial condition but not boundary conditions, and then IVPs, so initial boundary value problems. Typically for initial value problem, the spatial domain may be the whole real number line, so you wouldn't have boundary conditions. Okay, so we can write down 4 PDEs that vary only in the spatial derivative. So UT is UX, UXX, XXX, finally UXXXX. So fourth derivative with respect to x. So, and we've seen some of these equations before. So UT equals UX, that is advection. So the solution is some function of x plus t. So it's going to have a propagation to the left. Here we have an heat equation. This equation I haven't mentioned before. It's called Aries equation. And then I don't have a name for this equation. It's actually not a thing. You'll see why when we look into these problems further. Okay. So the domain for all of these is the whole real number line and t greater than 0. So we'll have some initial data specified at t equals 0 and try to solve a problem for all time in the future. Okay. Now, when you have a problem defined on a real number line, what we can do is solve the problem using Fourier Transform. Okay, and often referred to as the continuous Fourier Transform when there's a need to distinguish from the discrete Fourier Transform, which we'll see later on. Okay, so now Fourier Transform is written in different ways in different books. This is a convention that we'll use. The growth by infinity to infinity, e to the right. Behind x at of omega t omega. And u hat of omega t is also defined using a similar integral. We just need a factor of 1/2 pi out front. Means from minus I omega x u of x t x. So really, this is the continuous Fourier transform that takes a function of x and gives you a function of omega. Now, the function you're transforming may have other variables, independent variables that go along with it, like t here, that passes on through. But the focus is on the spatial variable. So u of xt is a function of xt that we refer to that as a function in physical space. X is meant to refer to something in the real physical world. And the output of the Fourier transform is this function, u hat of omega t. It's a function of omega, which refers to a frequency and also time. So this is called a function in frequency space. So that's what the Fourier transform and inverse transform do. They let you go back and forth between physical space and frequency space. Also known as, there's a frequency space is also referred to as Fourier space, but I think frequency is more descriptive. Okay. All right. Now, what we're going to focus on is a different sort of initial value problem, where instead of having the domain be the entire real number line, we're going to focus on a bounded interval, but with periodic boundary conditions. So when it's periodic, it's actually a convention to not really think of it as an initial boundary value problem, because normally with boundary conditions, you're specifying that u or some derivative of u is equal to something on the boundary. But here we're just saying we're extending u periodically. So for the rest of this discussion, I'm going to focus on that kind of initial value problem where it's periodic. But I want to make you aware of the continuous Fourier transform as well. Normally for numerical methods, you're not going to deal with a problem that's defined on the entire real number line, because if you're in computation, everything needs to be finite. And what people spend a lot of time doing is, if they have a problem that has defined an infinite or semi-infinite domain, and they want to solve it numerically on a bounded domain, well, we need some kind of boundary condition. And the original problem won't have that, because that was defined on an infinite domain. And you have to be very careful that you select a viable boundary condition. If you select the wrong one, you may get bad behavior. Like suppose you have problem defined on minus infinity to infinity, and you limit yourself to a certain interval, and let's say it has propagating waves. Well, you don't want to have those waves propagating to the boundary and then reflecting back, because that wouldn't happen on the infinite domain. The waves would keep going. That leads to what are called absorbing boundary conditions, where a wave propagates toward a boundary and then gets absorbed into it. That would effectively simulate what's happening in an infinite domain. Absorbing boundary conditions are very difficult to do, which is why we're not going to really talk about them here. But I want to make you aware this is something. This is a thing where we have a problem in infinite or semi-infinite domain, and we have to figure out what's a physical way to simulate it solve it on a bounded domain. A lot of people do use periodic boundary conditions for this, which can be okay as long as you don't have anything interesting happening near a boundary of a domain. And because again, you can get non-physical phenomena. I did some work on image processing where we considered imposing periodic boundary conditions, and we have to be careful about that because if you have an image as occupying your spatial domain and trying to do some processing to it, like removing noise or sharpening it, well, whatever is happening at one boundary of the image could affect what's happening at the opposite boundary, which doesn't make any sense. So what we did was we took the image and we padded it, like we reflected it across its own boundaries. So then the boundaries we now have don't really matter. We don't care what happens out there. So in that case, periodic boundary conditions is okay. So people like to use periodic boundary conditions when they can because they're easy to work with, for reasons that you'll see in a bit. You just have to be careful that you're not introducing nonsensical phenomena into the behavior of your solution. Okay, so how do we handle the case of periodic boundary conditions? I think I want to leave these PDEs up here. All right, so now I'm going to change my spatial domain. From minus pi to pi. And notice here I have less than or equal to. Here I have strictly less than. That's intentional because then there's no duplication. The value of the solution at pi is equal to the value at minus pi. Okay. So in this case, those periodic boundary conditions. So u of pi t equal to u of minus pi t. So then we use the discrete Fourier transform as opposed to a continuous. Now, this is as a continuous transform is defined using an integral from minus infinity to infinity. The discrete Fourier transform is defined using the integral over a bounded interval. So you can have t is 1 over 2 pi, integral from minus pi to pi e to the minus I k x. So that's t dx. So this is the discrete Fourier transform. It takes a function from physical space to frequency space. So the variable k, a parameter k, indicates frequency. Now, in the previous case, a continuous Fourier transform, I had omega. Omega was defined on the continuum. Omega goes from minus infinity to infinity, all the real numbers. K is an integer. All the integers from minus infinity to infinity. So then, when I want to go back from frequency space to physical space, I use the inverse Fourier transform. So u of xt is reconstructed using a sum instead of an integral. And this is called a Fourier series, which you would have seen in the prior PDE class. So this whole reconstruction of u of xt is the inverse. The discrete Fourier transform is abbreviated DFT. So this right here is the inverse DFT. Okay. Questions so far? All right. Now, all of these PDEs have the same form. UDT is some derivative with respect to x of a certain order of u. So I'm going to consider all 4 PDEs at once and show you how they can be solved. Okay. Okay. I have partial u with respect to t is equal to partial with respect to x applied n times to u, where in our examples, n is equal to 1, 2, 3, or 4. All right, actually, I'm going to rewrite it this way. Minus this equals 0. Okay. So what I can do is substitute the Fourier series. I'm assuming that u can be expressed by Fourier series. Why? Because a Fourier series is a 2-pi periodic function. And so is u. So u satisfies certain boundary conditions, periodic. So I'm writing u as a function that satisfies those boundary conditions. So,
Excuse me, sir.
sorry, what?
The second term, is it nth partial derivative of u?
Yeah, yes, it's the nth partial derivative of u with respect to x.
Okay, okay. I couldn't see it, that's all.
Okay. All right. Can you see it?
Just the numerator is slightly not clear.
Okay,
It's a bit unclear. Yeah. Okay, perfect.
Okay. All right. So, partial with respect to t of a Fourier series for u. Let's rewrite that. Minus partial with respect to x to the n of the same Fourier series. Equals 0. So now we need to carry out these differentiations. Fortunately, a lot of things simplify. First, we have the linearity of the derivative. So these summations I can pull out. Also, e to the ikx only depends on x. Here I'm differentiating with respect to t. So d dt is only going to be applied to this Fourier coefficient, u hat k of t. So what I have here is the sum of e to the ikx partial with respect to t of uk hats. Okay, for the time derivative part. And then over here, similar thing, we pull out the summation. And I'll have e to the now I have, this is the part, e to the ikx gets differentiated with respect to x n times. And then UK hat of t is treated like a constant because differentiating in respect to x. Right. Okay. Here's a key that shows us why, shows you why Fourier series are so nice for solving PDEs. Can anyone tell me, what do I get when I take the derivative of e to the I kx with respect to x? What does that get? What results from that?
Just the same term. Sorry, it will be multiplied by ik to the power n.
Yes. Yeah, when you take the n derivative. So now, okay, so that's ik to the n e to the I kx. So in both summations, we still have an e to the I kx, times something. So, and both summations are over the same indices, k going from minus infinity to infinity. So I can combine these into one summation and have e to the I kx. And then what's left? Over here I have partial respect to t of uk hat minus ik to the n uk hat. And all this has to equal 0. Oh, you know what? I gotta be more careful with my notation here. Okay, this is partial with respect to t because it's a function of x and t. UK has a function of only t, so that should be d dt. Oops. Okay, well, it does say this in my notes, but I forgot that. Now, what's nice about this is, okay, this whole summation must be equal to 0. Now, the reason why we can conclude that this part in parentheses must be 0 in each individual term is that the functions e to the I kx, so this set of functions, k going from minus infinity to infinity, are linearly independent. In fact, we can make a stronger statement than that. They are orthogonal with respect to the correct inner product, which is if you multiply them together, conjugate one of them, and integrate from minus pi to pi, that's the inner product of these functions e to the I kx. If you take the inner product of any two distinct ones, you'll get 0. But we don't even need that. This is enough to know that these are linearly independent. When you have a linear combinations of linearly independent functions set equal to 0, then by the definition of linear independence, the coefficient of that linear combination must also be 0. So this part of parentheses must be 0 for all t. So we end up with a system of like a one parameter family of ODEs. For the Fourier coefficients of our solution. And this applies for k for all integers k. So that's what the Fourier transform, discrete or continuous, does. It when applied to the spatial variables of a PDE, we actually get an algebraic equation in those spatial variables. So change the differential algebraic. We still have differentiation with respect to t, but that means in this case, our PDE in x and t got reduced to a system of ODEs in only t. And it's because of what happens when you differentiate e to the I kx with respect to x. All it does is multiply by this factor here. Because then we can go ahead and solve these ODEs put the solution back into our Fourier series for u of xt, and then we have u of xt. Any questions about what happened here? Well, leave the ODEs up. Okay. All right. We'll assume an initial condition. I should have written that earlier. U of x0 is u naught of x. Okay. So then you solve that ODE, uk hat of t equal to uk hat of 0 e to the ik to the n t. Where we get Fourier coefficients of the initial data by taking the discrete Fourier transform of the initial data u naught. So this is where our initial values come from. So now when we have this, we can take the inverse EFT or write the Fourier series. E to the I kx. And then I'll write what this is. So 0. Actually, I'll write this at the end. E to the ik to the n t. So this is our solution when we have periodic boundary conditions. Okay. So now we can consider the cases n equals 1, 2, 3, 4 and see how these solutions behave. Turns out the behavior will be very different. When n is equal to 1, we have what I'm going to focus on is the exponential part. So we have e to the I k x and e to the I k t. So it's e to the I k x plus t. So this is the interesting part of each term in the Fourier series. So when t equals 0, you just have e to the I k x. But once you go to t greater than 0, you have e to the I k x plus t. So so the question is, how does this function behave over time? So you're starting with just plain old e to the I k x. How does it change over time? So how does this change over time? Starting from e to the I k x when t equals 0. How does this behave?
Exponential growth?
No. Because if e to the I times something, e to the I times any real number always has a magnitude of 1. So it won't grow, and it won't decay either. And how does the graph of this relate to the graph of e to the I k x? We talked about this kind of thing before. And if instead of x, you have x plus t, what does that do to the graph?
Translates it t values to the right.
Almost. To the left, because of a
To the
plus.
left, yeah, sorry. Yeah.
Yeah. Okay. So what you have is a sum of waves traveling to the left with a speed of 1. And the speed comes from whatever's multiplying t here. It's just plain old t. So if there was a constant in front of t, that would be the speed of propagation. And all the waves travel together the same speed. So if you look at the graph of u naught of x, then over time you're going to see that graph shifting uniformly to the left. And that is advection. And so ut equals ux, that's an advective problem. Okay. Any questions about that one before we look at the next case? N equal 2. So e to the ikx, and then ik quantity squared is minus k squared. So e to the ikx, e to the minus k squared t. So what happens to this as t increases? You start with e to the ikx when t equals 0. Now it's multiplied by this. How does this factor behave over time? Yeah.
Show decay.
And the larger k is, the more rapid the decay. So now the effect of that is smoothing. Because if you think of this, e to the I k n to the t for whatever value then, as part of the Fourier coefficient. All right, so that's what we have here. Think of Fourier coefficients of u of xt. The faster these coefficients go to 0 as k goes to infinity, the smoother the function is. Well, if you're multiplying this Fourier coefficient by e to the minus k squared t, that's infinitely smooth. So, it has a smooth. So even if your initial data u naught of x is not smooth at all, even if it has discontinuities in it, u of xt in this case will be smooth, and it gets smoother and smoother as time increases. All right. So this is an example of diffusion. Just like the temperature groups, the temperature profile smooths out over time. And that's what we see here in this function. Okay. Any questions about that one? N equals 3. Different phenomenon. So here we have e to the ik. So ik cubed, that's minus I k cubed, because I cubed is equal to minus I. So I get so I'm going to factor out ik, and we get x minus k squared t. So what happens in this case? This is quite different than from the other two. But we consider each wave individually. I think in terms of a fixed value of k. How does this function behave? It starts out as e to the ikx when t equals 0. But how does it behave as t increases? It is going to move to the right. What's the speed? It's a k squared because that's multiplying t. Now, here's where it differs from over here. Here, all waves have the same speed. Here we have go to right, and we have speed k squared. That is called dispersion. Because you have high frequency waves traveling much more rapidly than low frequency waves. So the frequency content of u naught of x gets scattered. The amplitude of these waves does not change because the absolute value of this whole factor here is 1. But it's so we're not moving in the n equals 1 case, the waves are moving in lockstep. Here, you're doing your own thing. So the high frequency crowd wants nothing to do with the low frequency crowd or thing out here. Questions about that one? All right, so we have advection, diffusion, dispersion. So different terms describe physically what happens in each solution. And finally, n equals 4. I'm going to write those terms here just so you have them all in one place. Advection, diffusion. Okay. N equals 4. So now you have e to the I kx, and then I to the 4th is equal to 1. So that's e to the k to the 4th e. So how is that going to behave as t increases? Yeah, exponential growth. Okay, so this is why this PDE doesn't have a name. It doesn't describe any physical phenomena. You would want any physical phenomena behaving like that. That'd be straight out some sci-fi movie. One of those apocalyptic things, I guess. Now, when we have a PDE whose solution behaves like this, what do we call that kind of problem?
Ill-conditioned?
Close. That's the numerical analysis term. So the corresponding term in this area is ill-posed. Because this solution does not depend continuously on the data. So it does have a unique solution, so it passes the first 2 Hadamard conditions, but it fails in the third. Okay. It can also be referred to as unstable because of that growth, but I think ill-posed is a more rigorous term here. Okay, so questions about any of these 4 cases before I talk about the generalities. All right, so when we have particularly simple PDEs, linear PDEs, we have constant coefficients. what we can do is we can assume the solution has a certain form, u of xt is equal to e to the I kx, e to the I omega t, where omega is unknown. Now, when you have periodic boundary conditions, this can be a solution. Really, the general solution would be linear combination of these, and a specific linear combination would depend on the initial data. But you can assume a solution of this form to get a handle on how the solution is going to behave. So what you do is you substitute this form into a PDE, and you solve for omega. And what you get, omega is generally going to depend on k. So you get an equation that is called a dispersion relation. So the dispersion relation tells you what kind of behavior you can expect from your PDE. Now, your dispersion relation might not signal dispersion specifically. It could be any of these phenomena like advection, diffusion, exponential growth, etc. But it's called a dispersion relation. What you also get, you get what's called a growth factor, which is e to the I omega t. Because if you think of your initial data as a collection of waves, like a Fourier series, we have a Fourier coefficient times e to the I kx. But now that's going to get multiplied by this e to the I omega t, which may cause growth, it might cause decay, or maybe it doesn't change in magnitude at all. So this is very important to know too, to get an idea of qualitatively how your solution will behave. Okay. So what I'll do now is write down certain PDEs, excuse me, and show you how to get the dispersion relation, and then from there you can get the growth factor. Okay, so first the PDE that was shown you before but I've not discussed today. Wave equation. That's UTT is equal to c squared UXX. So what you do is you substitute e to the I kx, e to the I omega t in here, and let's see what you get. So the second derivative with respect to t is going to give us minus omega squared e to the I kx, e to the I omega t. So this is the UTT part. And then that is equal to c squared times UXX. Well, that's going to multiply this by IK quantity squared, but that's minus k squared. That's UXX. So now you want to solve for omega. You have a lot of cancellation, like the e to the I kx cancels out, the e to the I omega t cancels out. And you end up with omega squared is equal to c squared k squared. So omega is plus or minus ck. So what does this tell us? When omega is a constant multiple of k, that's when you have advection. But constant multiplying k indicates the speed. Plus or minus indicates the direction. So we actually have waves propagating in both directions. If you remember for wave equation, D'Alembert's solution, at as f of x plus ct, f of x minus ct to have waves propagating in both directions. So a dispersion relation reflects that. The growth factor that's e to the I plus or minus ck times t. And you take the absolute value of exponential growth or decay, but that's 1 because you have e to the I times a real number. Well, that's always going to be have a complex value of modulus 1. So there's no growth, there's neither growth nor decay in this case. Questions on this one? Here's one that's convection diffusion. So that's ut is equal to cux, that's the advection term, plus duxx. That's the diffusion term. So you substitute this form of u of xt in here, and we see that we're going to get a multiple of e to the ikx, e to the omega t. It's what's multiplying them that matters. So I'm just going to write that down. So you're going to get, from the first derivative, you're going to get I omega. Here we're going to get c times ik from a first derivative. And then here from the second derivative, we're going to get d times quantity ik squared. So it's going to be minus dk squared. So here is where you get your where you get your vertical relation. I can multiply by, I can divide through by I. So what will happen here is omega is equal to ck, and then dividing by I is same as multiplying by minus I, so plus I d k squared. Oh, wait, something's wrong here. Maybe my notes are wrong. Yeah, my notes are wrong. My notes have a minus throughout here. Okay. So then what happens is, if we look at the growth factor, we get e to the I omega t, but that's e to the I ck times e to the I times I is minus 1, so minus dk squared t. And this goes to 0, because this part remains constant in magnitude 1, but we have e to the minus dk squared t, that goes to 0, as exponential decay. So we have both advection and diffusion, but diffusion is going to win out. It's going to cause smoothing in the solution, even though there's also propagation. So we do have propagation with speed c, but you have smoothing going on at the same time. So notice it's similar here, like the leading term is the same. About here we have plus or minus, here we just have c. So here we have advection in one direction. So that would be to the left. And then we have this diffusion happening here. Questions about that one? Oh, wow, I'm out of time. Well, I'm actually surprised I filled the time even by going off script. Okay, so we got one last thing, sorry. and it's in the notes, but it's an equation I hadn't talked about, Schroding Verification. Don't forget the accent mark. So that's a strange one. We have I ut is equal to uxx. So for dispersion relation, we're going to get I times I omega from first derivative is equal to minus omega squared. So you end up with, once you simplify, omega, oh, sorry, not omega squared, k squared. So you get omega is equal to k squared. And because omega is a quadratic function of k, that is dispersion. So when omega is a linear function of k, that's always traveling the same speed. When it's a higher degree of polynomial k, we have waves traveling frequency dependent speeds. In this case, it means dispersion. The growth factor, so absolute value of e to the I omega, but omega is k squared t, but that is e to the I times a real number, magnitude 1, so there's neither growth nor decay in the waves, just this dispersion. All right. Okay, I'm done. Yeah, there's a couple more examples in the notes, but those are PDEs that I already talked about, so I didn't repeat them. For the first homework problem, you'll have a PDE like this, only more complicated. And you find the dispersion relation using the exact same approach. You just get something a little nastier, but you analyze it in the same way. So that's why I put out hints.
Excuse me, sir.
Sorry, what?
I had a little question.
Okay.
In the notes, the Schrodinger says omega equals negative k squared. Is that just a misprint?
Oh.
Because even I got omega equals k squared.
You know what? I see the problem. Dang it. Okay. Well, so here's the problem. When I made the initial assumption about dispersion, wrote e to the ikx, e to the omega t. In the notes, it's e to the minus I omega t, e to the ikx. So that's why all dispersion relations that I wrote are negative of what are in the notes. Now, for this one, it didn't matter because you have plus and minus. Okay, shoot. I'll have to clean this up next time. So.
However, the correct one is with positive I omega t, right?
Well, that's something I'm going to check out because I find having the minus in here a rather strange assumption, but I have to go with convention. How do people really define it? So what I'm going to do is I'm going to look up in a different source, and we'll go with that.
Okay, thank you.
Thanks. Oh, dang it.
All right, thank you.
It's funny how the scripted thing goes wrong.
Thank you, sir.
Yep.